Hello all. So in last lecture we have seen the perceptron learning algorithm, and then we have seen that the argument of proof from this. I have cited this PDF from the Columbia University, and we have seen that if there are two sets, right, and they are linearly separable, then the perceptron learning algorithm will converge in finite number of steps, and we have seen that this is how it converges, right? So now let's look back to all the questions again for the MP neuron. So we have seen that for time being, just ignore the highlighted ones, that is first and the last. But let's see the second and the third one. So in the second one, it says that only binary inputs can be applied. So I'm talking about the MP neuron, right? So, and we asked that what about real inputs? And perceptron can help us because in perceptron, real inputs are allowed, right? And also, we have seen that the inputs are weighted because we can give weights to the inputs, right? And so, this is really helpful in real life scenarios where you have to give more weights to some features while deciding something, right? For example, our movie tonight or not. So, whether it's weekend or not, or whether we have more money or not, we will weight money as a factor, right? Weekend is a different thing, but if we don't have money, we can't, right? So that's how this copes up with the real life situations and the problems. And the third point says that we have to decide the threshold, right? By in MP neuron, we have to just do it by trial, right? We have implemented our logic gates, right, which using just trial like and or, right? But now we have our learning algorithm. So perceptron not only gives the weights to the inputs, but it also gives the learning algorithm to learn those weights, right? Now let's come back to first point, that using single MP neuron we can implement Boolean functions which are only linearly separable. But what about non-linear? So that's what the last point says, that what about non-linear separability? Is it possible using perceptron? Using MP neuron, it's not for sure. But what about perceptron? Is it possible to implement XOR? Because we know that XOR is, right. I can again show you that in XOR, 2 points are here and two, right, 2 points are here. So there is no single line which can classify cross and zeros, right? Because we know that XOR for 0 0 it gives 0, and for 1 1 as well it gives 0. So this two are belongs to same class, whereas for 0 1 and 1 0 it gives 1. So this two belongs to class 1. So it's not possible by any single line to separate this cross and zeros perfectly. So we need some non-linear boundaries for it. But here is a catch, that it's not possible with single perceptron because there is no linearity, non-linearity that is being involved yet in perceptron. But if we can have a multiple perceptron, right, it's possible. And how? Let's try to see that. So again, this is the same XOR problem which I just explained here. But now let me go to the original article where it explains everything. So how this XOR problem is being handled. So if the credit goes to this article from towardsdatascience.com. So again, this is the perceptron. So let's see the agenda that we will see with the single layer perceptron, which we have already seen that it's not possible. Then we will see multiple distribution boundaries, maybe it's possible. And then we will see multi-layered perceptron, which is MLP in general. So let's try to see step by step. And the hands-on session for this will be in a separate video, as I do for other videos as well. So because after or else the video will be so long. So again, let's continue that we know that this is a weighted sum. How the output is calculated for a single perceptron. This is just a weighted sum, and then the bias. So what we do is we usually, like, to get the non-linearity, we use this function. The way after the weighted sum, we use this function as a non-linear function, but for time being we won't. So here this function allows us to fit the output in a way that it makes more sense. For example, in case of simple classifier that we have, an output of say minus 2.5 or 8 doesn't make much sense, right, with regards to classification. But if we do something like sigmoidal activation function, which will range everything from 0 to 1, then we can say that, okay, this, if it's 0.9, then we can say that there is a 0.9 probability that it belongs to this class, right? In the binary class, it belongs to class 1 because it's near to probability high, right? So it says that it's interpreted as a probability of the data point belonging to the particular class. So even though there are many activation functions, as I said, like there are sigmoid, ReLU, all these are nonlinear activation functions, but for time being, we are just using linear activation function, right? So we'll be using a simple linear activation function, right? For time being, we'll see how nonlinear will affect and so on. So we need to find this theta, and generally this threshold is set to 0 for perceptron after this weighted sum, right? So if it's greater than 0, we'll say that it's belongs to class 1. Here it says class 1 and class 2. So how the training algorithm works? So we have seen in our slide that I can also show you again, that in our one of the slides, I guess there was a learning algorithm here. Yes. So in the perceptron learning algorithm, I have shown you that we have to, in order to get the new weight, right? We have to, so this says that W new equals to W old plus something, right? And in this case, then it should be minus. So it's like we are updating W either by with the addition or subtraction based on whether it belongs to positive class or negative class. But let's see what we mean precisely with this. So here what we are doing is it's the same thing written here, that W new, it's W updated equals to W old plus something, right? Now what this something is like, it's a basic intuition that when the actual value and the computed value, right? Actual value we know from our ground truth table of XOR, and the computed value which is being computed by our perceptron. If they are same, then this delta W will be 0. So this entire term will be 0 and there is no update, right? So updated one will be same as the old one. But if it's non-zero, then we are updating something. And this LR is called learning rate, right? So learning rate, why it's called learning rate, that how fast or how often we have to update this, right? If this number is so high, then it will update so fast and there will be a zigzag motion. If you plot the graph of the weights, then it will be like continuously changing, right? So usually we keep learning rate as really less, like 0.01 or 0.0001, something like this in practice. And it's also hyperparameter. You can try different things and check whether it's giving good output or not for particular case. But there is something, so for timing, just assume that this is like the same thing that I showed you. So what's the 2D XOR problem? Again, the XOR truth table, and this I already drawn a couple of times, that this 2 points belongs to same class and this 2 points belongs to same class. So here red belongs to 0 and green belongs to 1. XOR, this is a symbol of XOR, nothing much. So a single layer perceptron, we know this. So we'll just write, so why this AND, NAND and these things are written, it will be clear in this article. But yeah, so what we are doing is we don't have to go through this code. So what this code is doing is that in the training function, what they are doing is something like this, that yeah, so they said that firstly there was one important point that I have to discuss, and that point is that yes, to train our perceptron here, we must ensure that all the training data points, that is 0 0 0 1 1 0 and 1 1, should be perfectly classified while training only, right? And but note that this is different in case of neural network. If you have seen or trained any neural network, we also have something called as training accuracy, where it's not 100%, right? So it's like, in case of perceptron, we must train a network such that it classifies all the data points in training set perfectly. Whether it's in neural network, right? It's not like this. It's okay if we have little less training accuracy, right? If we have it's 100%, then it leads to overfitting. We'll see what overfitting is, but as of now, you know what I mean. So for that, and that's why, so what they wrote, it's a really big code, but it's nothing dangerous here. So what they wrote in the training, that firstly, to train a single perceptron, single layer, firstly they are just initializing the counter of correct numbers. Then they say that if the counter is equals to the training data, which is 4 here, right? 0 0 0 1 1 0 1 1, then break it, or else don't break it, just continue. So if output and target are same, then we can say our correct counter is incremented by 1. Else what we do, reset the counter. So it will be like an infinite loop, right? Because we know that a single perceptron can't classify all the 4 data points correctly, right? So it won't happen, and every time counter will be reset, and then this will continue. And this all other functions are nothing scary, but just what I said, expected minus output into node, which is just the value of the node. You can just read the article and you will get it. And this is weight update rule, so which I showed, like old equals to learning new plus or equals to, so we are updating. And this is the gradient, right? What is expected, and so it's a delta w in short. This is the forward function that we do dot product w1 x1 to w2 x2 plus bias term. And when we classify that, when our forward function, right, if it's greater than 0, then we say it's belongs to class 1, right? And if not, then it belongs to class 0. So that's how it goes, nothing much. And this is just for plotting, so nothing important about this. And we are just putting a perceptron class here. So just to bring everything, all the piece of codes together, we are just creating a simple class, right? And so all this thing stuff goes here. So all these are now the methods of this class perceptron that we already seen. And now here we are training. So if we train our perceptron just with the target, so now we are training on the data set, which is of XOR data set. And as I said, like only 2 points can be classified correctly at a time. All 4 won't be, so it will go infinitely, right? So it's written here that it's clear that something should be written here. Remember that a perceptron must classify the entire training data set in one go. So if we keep track of how many points it correctly classified, we can get something like this, that it's, so at a time maximum 2 points can be consecutively correctly classified, not more than that, right? Rest are just 1. So it will just reset every time the counter, so it will again go to 0, as you can see in the graph, and then it just zigzag like this. So the algorithm only terminates, as I said, when it hits the counter 4, and which is not possible, right? And by 4, because we have 4 possible inputs, 0 0 up till 1 1 for a 2 input case binary. So it will go indefinitely for in a while loop, right? So here is the need for nonlinearity, that we need some decision boundary like this. And until now, we don't have any nonlinear functions in our weighted sum, right? It's just w1 x1 w2 x2. We don't have any nonlinearity that we need for such decision boundary, right? So what we can do, let's try one more thing, that we know that XOR can be written as something like this. Wait, what all these things are? So XOR can be implemented as the OR function and NAND function. If we just do the AND operation of OR and NAND, we will get XOR, right? So it is possible. So that's why they showed here how to implement. So all this big code here are just for implementation of OR function. So here you can see that all 4 inputs are classified, so it will stop here. So this is just for OR. And similarly for AND, so this is the decision boundary for OR. We know that it will be 1 if any of the input is 1, only 0 when it's 0 0, right? We know this about. And for AND, it's the other way around, right? So even you can see that in the AND case, it's classifying all 4 once, and then it will terminate the training. So can we bring back together something like this? Yes. And then this is how, without using nonlinearity, we can implement XOR function. And then you will see that also when we combine this, then we get this boundary which we want. So we will get 2 boundaries right now. So even though it's not nonlinear boundaries, just we are getting 2 boundaries which are separating this, right? So it's possible without XOR problem can be solved without using any nonlinear activation as of now, right? But though our model works here, right, this is really important, it doesn't seems like a viable solution, right? Because in our real life scenarios where we have most nonlinear classification task and the regression task, we'll see what regression is. If you don't know, don't worry. Then it's, this solution is really case specific, right? Because this is like we are doing some hack to just find this. And most problems can't be split into just simple intermediate problems like we did here. And then we can combine all of them to solve the big problem. So for something like this, right? If the data points are something like this, it's not possible even with two boundaries or three boundaries. It's not possible. We need something like this in such a case. And this is only possible when we have a really general model which can implement non-linearity, right? And that can be solved with the sigmoid neuron. And then drastically we will go to MLP, which is multi-layer perceptron. So we need to look for to a more general model which will allow for non-linear decision boundaries like a curve, as in the case above here. So let's see how MLP solve this issue. But I won't go to MLP straight away. I'll just give the motivation that why going from those harsh thresholding, right, and gradually smoothing up to a non-linear boundaries can help. So I'll just give some intuition behind this non-linear bound activation functions, or we can say non-linear boundaries, and then we'll slowly graduate to or uh, gradually go to this MLPs, right? So I won't go from this point, the MLP section, to downwards, but I encourage you to go through the entire article. It will be easy now after watching this video. And then after this attempt, we'll see that we can perfectly classify and also we can train this. So we'll do all these things and we'll see that how we are getting a perfectly nonlinear boundaries. And we'll also see that what happens if we add more number of layers and nodes, and also how the loss function affects this. So we'll stick to this because it's really important for entire neural network series, because this is a basic and base fundamentals that we need to grasp it nicely so that we can cover rest of the topics going to feed forward neural network and backpropagation, everything easily. So that's all for this video, and we'll continue from this point where we left. So next lecture will be on sigmoid neuron, where we'll see that how perceptron, just single perceptron, can be changed to sigmoid neuron by just using a sigmoid activation function. And then we will go to a network of such nonlinear activation functions, and we'll see that how we can classify a really complex data set. We'll see MNIST data set, right? And we'll see how its classification can be done. So stay tuned and thank you.